Hey everyone, we're continuing with user-defined data types. We've already learned how to create structures and enumerations. The next user-defined type we're looking at is the enumeration. So what is an enumeration? An enumeration is a special data type that lets you define a set of named integer constants. In simpler terms, it's a way to give clear, meaningful names to fixed numbers so your code becomes easier to read and safer to work with. For this lesson, I want to structure it like this. First, I'll show you everything about how to work with enumerations, and only after that, I'll answer the question of why we actually need them. Just like with structures, we can declare enumerations, define enumerations, and create enumeration objects. Let's start with the syntax for declaring one. You write the keyword enum, then the name of the enumeration, and a semicolon. The only new thing here is the keyword enum, which is short for enumeration, just like struct is short for structure. Why do we even need to declare enumerations? For the same reason we declare unions, structures, and functions. You might come across a separate enumeration declaration somewhere, but honestly, it's extremely rare in real-world programming. It can show up in multi-file projects, but we haven't worked with those yet, so let's move on. What really matters is defining an enumeration. Since an enumeration is a data type, we need to describe it first. We again start with the keyword enum, then we give the type a name. I personally name all my enumerations using Pascal case, but you can follow whatever style you prefer, just stay consistent. After that, we open curly braces and start writing a list of enumerators. So what is an enumerator? It's simply a named constant of an integer type. By default, its type is int. And this way, separated by commas, you can list as many such constants as you want. All of them will belong to the enumeration type. Just to give a clean definition, an enumerator is a named constant that belongs to an enumeration type. An enumeration may technically have no enumerators at all, you'll almost never see that. It may have one enumerator, also rare, or it may have two or more. You'll notice that enumerators in my Visual Studio are highlighted in a yellowish color. Yours might look different, but you can change that in the settings. After listing the enumerators, we close the curly brace and put a semicolon. We ended definitions of structures and unions in a similar way. And that's it, the enumeration type is created. Now you can start using it. So how do we actually use this? First, let's work only with the enumerators. Think of them as a list of regular integer constants you created. Because of that, you can use these constants anywhere you'd use numbers, print them to the screen, plug them into expressions, whatever you need. When you print them out, you'll see their values. By default, here's how it works. The first enumerator gets the value 0. Each following enumerator gets a value that's one greater than the previous one. But you can change the values of enumerators yourself. All you need is the assignment operator and the value you want. And you don't have to assign a value to every enumerator. If you assign a value only to the first one, then all the others will follow the usual rule. So if the first one is 10, the second will be 11 and third 12 and so on. You can hover your mouse over them to see their values. And if you assign a value only to the second enumerator, the rule still applies. The first will get 0, the second will get your custom value, and the third will be 1 greater than the second. You can also assign an enumerator the value of a previous enumerator. In general, the value of an enumerator must be constant, something that can be computed at compile time. For example, you can declare a global constant earlier and use it to set an enumerator's value. What you can't use is a variable, because variables are only known at runtime. Here's something important. When you define an enumeration with enumerators, you can use those enumerators without specifying the enumeration type. But you can also specify the type if you want. For example, in the example below, I print the values while explicitly writing the enumeration type and using the scope resolution operator. That way, you make it clear in the code that these enumerators belong to that specific enumeration. But because you can use enumerators without specifying the enumeration, there's a potential problem. You can't reuse the same enumerator names in different enumerations. If you try, the compiler will complain and tell you that you're redefining an existing enumerator. So each enumeration has to have a set of enumerators with unique names. But there is a way to solve this problem, and I'll show it very soon. But before we move on, let's talk about the underlying type of an enumeration. An enumeration is a set of integer constants, which means enumerators can only store integer values. But what kind of integer? By default, the underlying type is int, but you can change it. To do that, after the name of the enumeration, in its definition, you put a colon and specify the type you want. The allowed types are char, signed char, unsigned char, short, unsigned short, int, long, unsigned long, long long, and unsigned long long. In most cases, you don't need to set the underlying type manually. Now that we're done with enumerators, let's talk about enumeration objects. Since an enumeration is a data type, you can create variables of that type. Constants, arrays, pointers, references, and so on. Here I created an enumeration called weekday, which has 7 enumerators. Each one represents a specific day of the week. Below that, I created a variable of this enumeration type. First, it's stored on the stack. Since the underlying type is int by default, it takes up 4 bytes in memory. Second, it's uninitialized. So if you try to read its value right away, you'll get a compile time error. Because this is a variable of a special type, you can't assign it a value of just any other type, even if that value is something like 40, which technically has the same type as the underlying type of the enumeration. This is done for safety, because the whole point of an enumeration is to give you a set of named values and nothing else. So below, I can assign my object an enumerator of this enumeration, since both have the same type, weekday. But how does cout know how to print an object of a type you created yourself? With structures, this didn't work, because they contain multiple fields. Same with unions. But here it works. The reason is that both an enumerator and an enumeration object are implicitly converted to int when you print them. That's why you see the value 0. And since this is just a variable, I can change its value to another enumerator and you'll see a different value printed. You can also assign any integer value to an enumeration object if you use an explicit typecast. In that case, you're basically telling the compiler, don't worry, I got this. And the compiler allows it. For example, here we assign the value 5. Do we have an enumerator with this value? Yes, that's Saturday. So you can say that's what we're assigning. But technically, since this is just an object occupying 4 bytes of type int, you can assign any value of type int as long as it's within the range of the enumeration's underlying type. That's why we can assign 100 here, but you really shouldn't do that. It can easily lead to logical bugs. The point of an enumeration in C++ is to give you a type that stores a limited set of constants. So the common practice is to assign only valid enumerators, or values that you know correspond to actual enumerators, like the number 5 in our example. Below that, I created a constant of this enumeration type. It must be initialized immediately, otherwise you'll get a compile time error. Then we have an array of enumeration variables, also initialized. Next comes a pointer and a reference to the enumeration. And of course, you can place enumeration objects on the heap, on the stack, or in static memory, exactly the same as with any other data type. These traditional enumerations have 2 problems. First, their enumerators are visible in the global scope. That means those names are already taken and you can't reuse them anywhere else. The second problem is that both enumeration objects and their enumerators are implicitly converted to an integer type. Sometimes a programmer can forget about this, and that can lead to bugs. Because of that, there is a more modern and safer way to write enumerations by using the combination enum class or enum struct. What's the difference? Here I created 2 enumerations. The first one is the kind you already know. The second one represents some kind of direction. And here I added the word class. Look below. You can create objects of both enumeration types the same way, but you cannot use enumerators from an enum class enumeration directly because you must always specify the enumeration they belong to, like this. This immediately solves the global visibility problem. The enumerators are now hidden behind the enumeration. The second improvement is that enum class doesn't allow implicit conversions. Regular enumerations are implicitly converted to an integer type, like you saw earlier, but enum class enumerations are not. You must use explicit casting. This eliminates accidental conversions where a programmer forgets that something is an enumeration. With explicit casting, you always know what you're dealing with. The same goes for comparisons. When you compare an enumerator or an object of a regular enumeration with another type, it's implicitly converted to an integer. With enum class, that doesn't happen. If you want to compare it with another type, you must use an explicit cast. But you can freely compare enumeration objects with enumerators of the same enumeration type. That's why I recommend using only this newer form of enumeration instead of the traditional one. It's safer and it makes your code easier to read. Though you'll still see the old-style enumerations quite often, especially in older projects. You can also create enumerations without giving them a name. In that case, you just end up with a set of enumerators. You can use them the same way you'd use regular constants. You could create three separate constants with the same values, but sometimes it's simply shorter to write a small set of enumerators instead. Though honestly, this is pretty rare in real-world programming. Starting with the C++23 standard, we finally got a function that converts an enumeration value into its underlying integer type. Here I created an enumeration called caller and explicitly set its underlying type. Then, in the code, I create a variable of this enumeration and print its value using the function std_underlying. It takes an enumeration value and returns the value of its underlying type. At the moment, November 2025, your compiler most likely won't recognize this function by default because C++ projects are still set to build with a C++20 standard. To enable C++23, go into your project settings and switch the language standard to C++23. Why do we even need this function? Before, if you wanted to get the numeric value out of an enumeration, you had to write something like this. It looked clunky and wasn't always safe, especially if the enumeration's underlying type wasn't int and the programmer picked the wrong type when casting. That's why I recommend using this new function whenever you need to convert an enumeration to its underlying type, even though nothing stops you from using a regular explicit cast if you prefer. You already know that an enum class creates a strongly typed enumeration. This means its enumerators don't leak into the surrounding namespace. In other words, to use enumerators from an enum class, you must specify the name of the enumeration every time. Some programmers complained about this, so C++ added a special command that lets you temporarily open the enumeration scope, allowing you to use its enumerators without writing the enumeration name. For example, here we wrote using enum caller. This means that from this point to the end of the function, all enumerators of this enumeration become visible, so now we can write code like this. This is convenient when you don't feel like typing the enumeration name over and over in a small piece of code, for example inside a switch. Personally, I never found it tiring to write the enumeration name, and I think the code looks clearer that way, so I don't use this command. But here's something even more interesting. You can pull in a single specific enumerator instead of all of them. For example, you can write a command like this. You use the keyword using and write an enumerator together with its enumeration name. From this point to the end of the function, that one enumerator can be used without specifying the enumeration, while the others still cannot. This is even rarer in real-world programming, but it's worth showing anyway. Alright, that's everything about how enumerations work. Now let's talk about why we need them. Enumerations exist to make your code clearer, safer, and more logically structured. They let you replace meaningless numbers with meaningful names that describe a state, a mod, a type, or some specific option. Instead of working with numbers like 0, 1, 2, you work with names like idle, running, jumping. This makes your code self-documenting. You can see what's going on without needing extra comments. Enumerations also give you type safety. The compiler knows that a variable has a specific enumeration type, and it won't let you assign random numbers to it or compare it with something that doesn't make sense. That reduces the chance of bugs. They also make your program easier to maintain and extend. If you need to add a new state or option, you just add another item to the enumeration, and all the places that use it automatically become more flexible. And finally, enumerations make your code more expressive and easier to reason about, especially when you're dealing with branching, state logic, flags, or parameters that are supposed to take only a limited set of values. And that's the end of the lesson. Thanks for watching. I hope everything was clear and helpful. Don't forget to check out the practical lesson so you can reinforce what we covered by solving the real tasks. If you enjoyed the video, you can support me by leaving a like, writing a comment, subscribing to the channel, donating through the link in the description, or becoming a channel member to get access to the practical videos. See you in the next lesson.